Starship stands nearly 400 feet over the flat Texas coastline at Boca Chica. 33 Raptor engines at the base of the Super Heavy booster produce roughly 16 million pounds of thrust at liftoff. To put that in context, that's more than double what the Saturn V generated when it launched Apollo astronauts toward the moon in the late 1960s. It's also nearly twice the thrust of NASA's own Space Launch System, the rocket that just flew astronauts around the moon on Artemis II. SpaceX built Starship for one purpose above everything else: to carry humans beyond Earth, first to the moon and then all the way to Mars, where Elon Musk wants to build a permanent city of 1 million people. The ambition behind that goal is almost difficult to overstate. We're not talking about planting a flag and coming home. We're talking about a self-sustaining civilization on another planet, a backup for humanity itself, a project that Musk has described as the most important thing our species could possibly do with its time and resources. But as of right now, in April 2026, this rocket has never completed a full orbit. The timeline for Mars has been pushed back by 5 to 7 years, and the country that might actually land astronauts on the moon first may not be the United States. So what exactly is going on with SpaceX's plan to conquer the solar system, and can they actually pull it off before the window closes? Before we start, I want to tell you something. A lot of strange things have been happening in space lately, so subscribe to this channel right now, and I'll tell you even more secrets of space. And write in the comments below what you think about all of this. Nobody was paying much attention to the patch of scrubland near Boca Chica Beach back in 2014, when SpaceX first leased the land. A handful of modest homes, a wildlife refuge, and an empty stretch of Texas coastline that barely registered on a map. The place was so unremarkable that most people driving through would have assumed it was just another forgotten corner of the Gulf Coast. That was about to change in a very significant way. SpaceX began integrated flight testing of the full Starship vehicle in April 2023, stacking the Super Heavy booster and the upper stage ship together for the first time in history. The first attempt went about as well as you would expect for the most complex rocket ever assembled by human hands. The vehicle cleared the launch tower, climbed for about 4 minutes on a pillar of fire from 33 Raptor engines firing simultaneously, and then tumbled out of control over the Gulf of Mexico. SpaceX triggered the flight termination system, and the whole thing blew apart in a dramatic fireball that was, in its own way, spectacular to watch. Not exactly a confidence booster. The launch pad itself took serious damage too, with concrete chunks blasted deep into the surrounding wetlands from the sheer force of the engine plume, which triggered an FAA environmental review that delayed the next flight by several months. The second test in November 2023 went further. The Super Heavy booster separated successfully from the ship for the first time, and both stages flew independently before eventually being lost. Progress, even if the ending looked familiar. Then came the stretch where things started genuinely clicking into place. Flight 3 in March 2024 nailed the first successful stage separation and ship coast phase, demonstrating that the two vehicles could work together as a coordinated system, rather than just an expensive explosion waiting to happen. SpaceX also pulled off an internal cryogenic propellant transfer of about 5 tons between tanks aboard the ship itself. That 5-ton transfer doesn't sound glamorous on the surface, but it represented the very first baby step toward the orbital refueling technology that everything about the Moon and Mars plans ultimately depends on. The reason it matters so much is that Starship, as enormous as it is, cannot carry enough propellant to reach the Moon or Mars in a single launch. It needs to be refueled in orbit by a dedicated tanker variant, a process that requires successfully transferring hundreds of tons of liquid oxygen and liquid methane in the vacuum of space. That 5-ton test was the proof of concept that the plumbing and the physics could actually work. Flight 4, in June 2024, brought Starship through a complete re-entry for the first time. The heat shield held up against temperatures that can exceed 1,400 degrees Celsius. The belly flop maneuver worked as designed, and the ship survived all the way to ocean level before being intentionally lost on splashdown. And then Flight 5, in October 2024, changed everything. The Super Heavy booster launched, separated cleanly, flipped itself around through a precise series of engine burns, and flew back to the launch site at Starbase. Then it was caught mid-air by 2 massive mechanical arms mounted on the launch tower. SpaceX calls them chopsticks, which somehow makes the whole thing sound both casual and absurd, given what they were actually doing. Nobody in the history of rocketry had ever done anything remotely like that. Catching a 20-story booster out of the sky using a pair of giant robot arms looked like something lifted straight out of a science fiction film, and it worked on the first attempt, which was either a testament to meticulous engineering or one of the most audacious gambles in aerospace history, likely both. That was the high point of the Starship program's momentum, because what followed was a brutal stretch that tested everyone's confidence in ways that nobody had quite anticipated. Flights 7, 8, and 9, spanning January through May of 2025, all experienced significant in-flight failures. 3 consecutive launches, 3 consecutive anomalies. On top of that, Ship 36 exploded during a ground test at the Massey's test facility in June 2025. 4 serious setbacks in the span of just 6 months. Engineers, investors, and NASA officials were all asking the same deeply uncomfortable question. Can this program actually deliver on the timeline it promised? SpaceX's answer arrived on August 26, 2025, with Flight 10. All 33 Raptor engines ignited and performed flawlessly. In a deliberate show of confidence, the company intentionally shut down one engine during ascent to test how the booster handled a real engine-out scenario, simulating the kind of mid-flight emergency that any operational vehicle must be proven to survive. In the upper atmosphere, the ship executed a full re-entry, nailed the belly flop maneuver, flipped vertical, and splashed down softly in the Indian Ocean. SpaceX declared it a mission that met every major objective. That single flight did something numbers alone can't fully capture. It saved the program's momentum at the precise moment it needed saving most. Flight 11, on October 13, 2025, pushed the boundaries even further. This was the final version 2 Starship mission, and it was packed with firsts. The Super Heavy booster was flying for its second time, having previously launched on Flight 8 months earlier, marking another step toward the full reusability the program depends on. SpaceX deployed 8 Starlink version 3 mass simulators as a stand-in payload, reignited a Raptor engine in the vacuum of space to validate deep space propulsion capabilities, and deliberately removed some heat shield tiles on the ship to test a new felt-based thermal backing material under actual re-entry conditions. The ship came through re-entry intact and splashed down precisely on target in the Indian Ocean. So across those 11 flights, 6 were broadly successful, and 5 involved major failures or destructive outcomes. That sounds like a coin flip, and honestly, it is a coin flip. But each successful test expanded the envelope of what a fully reusable super heavy lift vehicle could actually do in practice, pushing the design closer to something that can be trusted to carry crew and critical cargo. The failures weren't just losses, they were data, and expensive data tends to teach the most. The real upgrade, the one that actually matters for everything that comes next, is now on deck. Starship version 3 is the variant that NASA needs, and the variant Elon Musk needs, to make any of the Moon or Mars plans more than a promise. It stands about 1.5 meters taller than version 2, and runs on the new Raptor 3 engine, which cranks out 280 tons of thrust with a specific impulse of 350 seconds, a meaningful efficiency gain over its predecessors. Version 3 is designed to loft more than 100 metric tons to low Earth orbit, compared to roughly 35 tons for its predecessor, a nearly 3-fold leap in raw payload capacity. And crucially, version 3 is the first variant built to perform orbital propellant transfer between 2 separate starships, the foundational capability that makes deep space missions possible, because no rocket yet built can carry enough fuel in a single launch to reach the Moon or Mars fully loaded. That capability is the single most important piece of technology, gating both the Artemis lunar landing and any future Mars mission. SpaceX was targeting a first version 3 flight from the brand new Pad 2 at Starbase with Booster 19 and Ship 39. The FAA had cleared SpaceX for up to 25 Starship launches per year from Starbase, a 5-fold increase that was granted back in May 2025. At the Star Factory production facility, Musk claimed in May 2025 that SpaceX could already produce a new ship roughly every 2 to 3 weeks, with an aspirational goal of eventually producing 3 ships per day, or roughly 1,000 per year. Now that number sounds completely insane, and it probably is, at least for now. But consider what SpaceX has already demonstrated with its existing fleet. The Falcon 9, the company's battle-tested workhorse rocket, flew 166 missions in 2025 alone, and had already logged 26 flights in just the first 2 months of 2026. That works out to roughly 1 launch every 2.5 days. SpaceX has already proven it can operate at a manufacturing and launch tempo that would have been dismissed as pure fantasy just a decade ago. The question is whether they can scale that same relentless operational intensity to a vehicle 10 times larger, 10 times heavier, and exponentially more complex in nearly every system that matters. Now let's talk about the Moon, because the politics surrounding this program are honestly almost as dramatic as the engineering itself. In April 2021, NASA awarded SpaceX a firm, fixed-price contract worth $2.89 billion to develop a lunar variant of Starship called the Human Landing System, or HLS. Subsequent contract modifications have added roughly another $1.15 billion on top of that. The HLS is a specially modified version of Starship, stripped of its atmospheric re-entry flaps and heat shield, since it will never need to punch back through Earth's atmosphere. Instead of returning to Earth, it descends to the lunar surface using specialized mid-body thrusters mounted around the ship's midsection, giving it precise control during the final approach to a world with no air, no runway, and very little margin for error. Think of it as a starship designed to travel in only one useful direction at a time, down to the lunar surface and back up to orbit. The mission architecture works like this. NASA launches astronauts aboard the Space Launch System rocket, tucked inside an Orion capsule. Orion carries the crew out to a special, near-rectilinear halo orbit around the Moon, a highly elliptical path that brings the spacecraft relatively close to the lunar surface at its nearest point, while remaining gravitationally stable. Meanwhile, a Starship HLS has been launched separately from Earth, refueled in low Earth orbit through a series of 10 to 15 tanker Starship flights, and then dispatched ahead to wait in lunar orbit, fully fueled and ready to receive the crew when Orion arrives. 2 astronauts transfer from Orion into the Starship lander, ride it down to the surface, spend about a week conducting moonwalks, then fly it back up to dock with Orion for the trip home. It's an unbelievably ambitious architecture, one that requires precise orbital choreography and a degree of spacecraft autonomy that has never been tested in a crewed lunar context before. Musk has claimed Starship HLS could deliver up to 200 tons of cargo to the lunar surface, which would be orders of magnitude beyond anything Apollo ever carried. For context, the entire Apollo 17 mission landed roughly 900 kilograms of equipment on the Moon. The scale difference is almost difficult to comprehend. Then, in February 2026, the entire Artemis program got torn apart and reassembled. Jared Isaacman, confirmed as NASA's new administrator in December 2025, announced a sweeping restructuring on February 27, 2026. Isaacman is the billionaire entrepreneur who flew on SpaceX's Polaris Dawn mission, a private spaceflight that included the first commercial spacewalk in history, which made his appointment as NASA chief controversial from the start. Critics question whether someone so deeply embedded in the commercial spaceflight ecosystem could objectively oversee a program that depends on companies he has personal relationships with. The changes he announced only deepened that debate. Artemis 3, originally supposed to be the first crewed lunar landing since Apollo 17, touched down in December 1972, got completely redesigned. Instead of putting astronauts on the Moon, it became a crewed low Earth orbit demonstration where Orion will dock with both the Starship HLS and Blue Origin's Blue Moon lander. Think of it as an equipment shakedown, a chance to wring out the systems and uncover problems before committing to a landing attempt. It's similar in concept to what Apollo 9 accomplished back in 1969, when NASA tested the lunar module in Earth orbit, verifying that it could separate, maneuver independently, and redock with the command module before anyone trusted it to do all of that 250,000 miles from home. The timeline for this docking test was moved up to mid-2027. The actual first crewed landing on the Moon got bumped to Artemis 4, now targeting 2028. And that wasn't even the biggest news to come out of the restructuring. The Lunar Gateway space station, which was supposed to serve as a permanent crewed outpost in lunar orbit and act as a staging point for surface missions, was canceled entirely. It had been a cornerstone of NASA's long-term lunar strategy for years, with international partners already committed to contributing hardware. Planned upgrades from the SLS Block 1 to the more capable Block 1B and Block 2 versions were also scrapped. NASA essentially froze the SLS rocket design at its current configuration and went all in on commercial landers from SpaceX and Blue Origin as the fastest available path to getting boots on the lunar surface. Just on April 27, 2026, Isaacman testified before the House Appropriations Subcommittee that Artemis 3 will not launch before late 2027, and that both SpaceX and Blue Origin have indicated they can support a docking demonstration on that timeline, with a landing attempt following in 2028. So here's where Elon Musk dropped a bombshell that surprised even longtime SpaceX watchers. On February 8, 2026, he posted on X that SpaceX would be shifting its primary focus to the Moon. He called for building what he described as a self-growing city on the Moon, achievable in less than 10 years. His reasoning was surprisingly practical for someone who usually gravitates toward the most audacious option on the table. He pointed out that you can only travel to Mars when the planets align in a favorable orbital configuration, which happens once every 26 months, and the transit itself takes roughly 6 months each way, meaning a round-trip commitment of over a year just in travel time alone. The Moon, by contrast, is reachable with a viable launch window every 10 days, and a travel time of just 2 days. If the goal is building off-world infrastructure and stress testing the technology needed to eventually sustain a permanent human presence beyond Earth, the Moon gives you dramatically more opportunities to iterate, to fail cheaply, and to learn. There's also a financial logic here that Musk didn't spell out explicitly. SpaceX has been advertising commercial cargo deliveries to the Moon starting in 2028, and to Mars starting in 2030, at a published price of $100 million per metric ton to either surface. That's a staggering figure, but for space logistics at interplanetary scale, it's also a number that serious institutional customers have apparently been willing to sign on for. The Italian Space Agency became SpaceX's first confirmed Mars-bound cargo customer back in August 2025. A milestone that signaled the commercial side of deep space exploration is no longer purely theoretical. A Moon-first strategy, then, isn't just an engineering detour. It generates real revenue and hard-won operational experience years before Mars becomes genuinely feasible. And with SpaceX reportedly preparing for what could be the largest private company IPO in history, demonstrating near-term commercial value from lunar services makes a great deal of sense from an investor perspective. Proving out the hardware and the business model in cislunar space before committing to the far more demanding Mars run is, arguably, exactly what a maturing aerospace company should be doing. The very next day, February 9, 2026, Musk confirmed that SpaceX's Mars settlement plans would be delayed by approximately 5 to 7 years. For anyone who has followed Musk over the last decade, this was a jarring shift, the kind of announcement that lands differently, depending on whether you've been a true believer or a skeptic all along. To understand why, it helps to go back to his famous 2016 speech at the International Astronomical Congress in Guadalajara, Mexico, where he laid out the philosophical foundation that has driven SpaceX since its earliest days. He argued that the future of humanity divides into 2 possible timelines. One in which we remain on Earth indefinitely and eventually face some kind of extinction event, whether through asteroid impact, runaway climate change, or any number of other civilizational threats, and one in which we become a spacefaring civilization spread across multiple planets, dramatically reducing the odds that any single catastrophe could end the human story entirely. He has called Mars a backup drive for civilization, and has said repeatedly that establishing a self-sustaining city there matters more to him than whether he ever personally sets foot on the surface. It's an explicitly long-horizon vision, one where the goal isn't adventure or prestige, but existential insurance for the species. So Mars has not been abandoned. It has been rescheduled. The original Mars plan, presented at a Starbase event on May 29, 2025, was staggeringly ambitious in its scope and timeline. The vision called for 5 uncrewed starships during the late 2026 Mars transfer window, loaded with Tesla Optimus humanoid robots, tasked with beginning surface preparations and early infrastructure work. That would be followed by around 20 ships during the 2028 to 2029 window, potentially including the first human crew. By 2031, the plan envisioned 100 ships making the journey, and eventually 1,000 or more vessels departing during every available Mars transfer window, each carrying between 100 and 200 passengers. The long-term target was a self-sustaining Martian city of 1 million people, potentially by 2050. It was the kind of roadmap that reads either as visionary or as wildly optimistic, depending on your disposition. And Musk himself estimated that the 2026 Mars flights had only about a 50-50 chance of happening, even before the delay was announced. With the Moon pivot now in effect, the realistic earliest window for an uncrewed Mars landing has shifted to somewhere between 2028 and 2029, and the first crewed Mars mission likely won't happen until 2031 at the very earliest. The technical challenges go a long way toward explaining why these timelines keep stretching, despite genuine progress on the hardware side. Orbital refueling remains the biggest unsolved puzzle in the entire architecture. Every starship headed to Mars needs roughly 1,200 metric tons of propellant loaded in orbit to make the trip. Each tanker starship can haul approximately 100 tons of fuel up from the surface, which means roughly 12 separate tanker launches, and 12 individual docking operations are required for every single Mars-bound ship. For the originally planned 5-ship fleet in 2026, That math works out to around 60 tanker flights that would need to be squeezed into a narrow and unforgiving launch window, a logistical challenge of a scale that has never been attempted before. As of early 2026, SpaceX has only demonstrated a modest 5-ton internal propellant transfer during Flight 3, back in March 2024. The gap between that proof of concept and the full operational capability required for Mars is enormous, and closing it will take time that no amount of ambition can simply compress away. Ship-to-ship fuel transfer between two separate starships in orbit has never been attempted, not even once. The heat shield presents another deeply open question. Musk has personally acknowledged that nobody has ever developed a truly reusable orbital-class heat shield, and that admission carries significant weight coming from someone who tends toward optimism. Earth re-entry is hard enough, demanding enormous engineering effort and still resulting in periodic failures. Mars re-entry is a different beast entirely. The Martian atmosphere is roughly 1% the density of Earth's, but it's composed of 95% carbon dioxide, which behaves more aggressively against thermal protection materials at hypersonic speeds. That chemical composition means the plasma sheath surrounding a descending vehicle interacts with heat shield surfaces in ways that aren't fully captured by Earth-based testing or simulation. Then there's the challenge of landing something this large on Mars. Every previous Mars lander, from the Viking probes to the Perseverance rover, weighed about a ton at most. Starship tips the scales at over 100 tons at landing. That's a 200-fold increase in mass, and the problems don't scale linearly. Planting a 50-meter-tall, slender vehicle vertically in the low Martian gravity, where the atmosphere is too thin for parachutes but thick enough to create real aerodynamic complications during descent, has no engineering precedent anywhere in spaceflight history. There is no comparable mission to look back on, no partial solution to borrow from. Radiation is the problem that keeps space medicine researchers up at night. A round-trip Mars mission takes roughly 2.5 years, and the human body has no natural defense against what it will encounter along the way. Data from the radiation assessment detector aboard the Curiosity rover showed that astronauts would absorb a minimum of 0.66 sieverts of cosmic radiation during that journey. That's enough to raise cancer risks significantly and potentially cause neurological effects, including measurable changes to cognition and memory that researchers have observed in animal studies conducted at high-energy particle facilities. Galactic cosmic rays are extraordinarily difficult to shield against with any material a spacecraft can realistically carry. Adding enough shielding mass to meaningfully reduce exposure would create its own cascade of engineering problems, and no fully satisfactory solution currently exists. And even if astronauts survive the trip and the landing, sustaining human life on Mars requires technology that doesn't fully exist yet. No one has built a closed-loop, bioregenerative life support system capable of operating indefinitely without resupply from Earth. The International Space Station, humanity's most sophisticated and long-running outpost in space, still depends on regular cargo deliveries to keep its crew alive and its systems functioning. Mars won't have that luxury, with a minimum 6-month supply chain, even under favorable orbital alignment. Every breath of oxygen, every liter of water, every calorie of food needs to either be manufactured on site using local resources or packed into the ship before departure, with enough redundancy to survive equipment failures, accidents, and the unexpected. And then there's the human factor that nobody in the SpaceX promotional videos likes to talk about. Long-duration isolation studies like the Hawaii Space Exploration Analog and simulation known as High Seas, and the Russian Mars 500 experiment, which locked 6 people inside a simulated spacecraft for 520 days, revealed a consistent pattern of psychological deterioration, interpersonal conflict, disrupted sleep, depression, and a gradual erosion of motivation and performance that no amount of careful crew selection has fully prevented. Documented serious psychological effects emerged with troubling consistency across isolation studies. Depression, interpersonal conflict, cognitive decline, and motivational collapse all showed up repeatedly in participants, regardless of how carefully crews were selected or how thoroughly they were prepared. These weren't edge cases or outliers. They were patterns, recurring across different missions, different nationalities, different personality profiles. An actual Mars mission would involve a crew sealed inside a metal cylinder for 6 months each way, living in a habitat roughly the size of a studio apartment, on a planet where stepping outside without a pressure suit means death in approximately 90 seconds. There is no emergency exit. There is no turning back once you're past a certain point in the journey. The psychological endurance required to sustain focus, cooperation, and basic mental health under those conditions is something science has barely begun to understand, let alone design solutions for. The plan for making Mars self-sustaining revolves around a chemical process called the Sabatier reaction. Carbon dioxide, drawn from the thin Martian atmosphere, combines with hydrogen to produce methane fuel and water as byproducts. It's an elegant idea in principle. The planet essentially provides the raw ingredients for its own return trip propellant. Mars has abundant CO2, and SpaceX's preferred landing site at Arcadia Planitia in the northern hemisphere sits above deposits of subsurface water ice, lying just centimeters beneath the surface. A pre-positioned propellant plant could theoretically manufacture fuel on site before any human crew even arrives. But independent assessments, including a 2024 study published in Nature, concluded that the surface power generation required, most likely nuclear reactors of a kind not yet built or tested in space, along with the water mining equipment needed to feed the process, are nowhere near the development stage that SpaceX's timeline demands. Musk has also floated the longer-term idea of terraforming Mars entirely, famously suggesting that detonating thermonuclear devices over the Martian polar ice caps could release enough carbon dioxide and water vapor to dramatically warm the planet and begin transforming it into something more hospitable. Peer-reviewed research, including a 2018 analysis published in Nature Astronomy, poured considerable cold water on that concept. Even if every molecule of CO2 currently trapped in Mars' polar caps and soil were released simultaneously, it still wouldn't generate sufficient greenhouse warming to make the surface genuinely habitable for humans. The atmosphere would thicken slightly, but not nearly enough. More recent research has explored alternatives: solar mirrors positioned in Martian orbit, engineered aerosols designed to trap heat, and synthetic biology approaches using extremophile organisms adapted to survive and slowly alter harsh environments. Each carries its own enormous engineering challenges, and even under the most optimistic scientific estimates, warming Mars enough to sustain liquid water on its surface is a process that measures in centuries, not decades. SpaceX is not building these plans in isolation. There is a genuine space race unfolding, and the competitor closing in fastest is China. China has been targeting a crewed lunar landing by 2030, and their program is moving with an urgency that has Washington paying close attention. The Long March 10 rocket, their heavy-lift vehicle designed to rival Starship's capabilities, represents a credible challenge that no serious analyst is dismissing. That competitive pressure has shaped how SpaceX frames its near-term priorities. Musk has pivoted the company's immediate focus toward establishing a permanent presence on the Moon, presenting it as a faster proving ground for the same technologies that Mars will eventually demand: life support, in-situ resource utilization, long-duration operations far from Earth. The Mars vision itself remains intact on paper: a million-person city, propellant manufactured directly from the Martian atmosphere, a civilizational backup plan standing ready in case something catastrophic befalls the only planet humanity has ever called home. It is an audacious picture, and Musk has never wavered in describing it as the animating purpose behind everything SpaceX builds. But the timeline has slipped by the better part of half a decade, and the technical gaps are real. Orbital propellant transfer, the critical capability that allows a fully fueled Starship to depart Earth's gravity well on an interplanetary trajectory, has not yet been demonstrated between two vehicles in space. Every independent engineering review of the program reaches roughly the same conclusion. The remaining challenges dwarf what the current development pace can realistically solve on Musk's original schedule. At his Starbase presentation in May 2025, Musk addressed this directly, arguing that progress should not be measured against arbitrary calendar dates, but against the longer arc of what the program is actually trying to accomplish: the timeline to establishing a self-sustaining civilization on Mars. He said each Starship launch is fundamentally about learning what is needed to make life multiplanetary, and that the vehicle will keep improving until it can carry hundreds of thousands of people to another world. Whether the schedule catches up to the ambition remains the open question that the entire industry is watching. Whether that happens in 15 years or 50, the hardware being assembled in South Texas right now represents the most ambitious engineering project in the entire history of human spaceflight. Not just in scale or cost, but in the sheer audacity of what it's trying to accomplish. A fully reusable, rapidly reflown heavy-lift vehicle, designed not merely to reach orbit, but to carry civilization beyond the cradle of Earth. With China closing the gap and America's entire lunar strategy resting on a rocket that hasn't yet reached orbit, the next 2 years will carry enormous weight. The decisions made in engine bays and launch control rooms along the Gulf Coast will ripple outward for decades. Either Starship becomes the vehicle that cracks open the solar system, enabling crewed missions to the Moon, permanent outposts on Mars, and a transportation infrastructure that makes deep space genuinely accessible, or it becomes the most spectacular, unfulfilled promise in aerospace history, a towering monument to what almost was. The pressure is real, the stakes are generational, and the margin for complacency is essentially zero. Every test flight, every anomaly, every hard-won lesson baked into the next iteration is a step either toward that future or away from it. As of April 2026, this story is far from finished. The final chapter hasn't been written, and the engineers, technicians, and mission planners working through the night in South Texas are the ones holding the pen. That's all for today. If you like space stories and want to stay up to date with new episodes, subscribe to this channel and turn on notifications. See you in the next podcast.